So in this video we're going to go over finding local extrema on a function. So here's the idea. If we have a function f of x, we remember that f of x represents the function outputs. So if we have a function f of x and it's defined over an open, not closed, an open interval centered at a, then we're going to define local maximum values and local minimum values. So here's the idea. We look at the graph of the function and you want to look for any points that look like they might be high or low points on the function. And the idea is, if directly under what appears to be a high or a low point on the function you have an input value, and we're calling that input value a, if you can define an open interval centered at a, that contains a, what we want to notice is that a is an input value. So this point right here is going to have an ordered pair associated with it. It's located at input a, output f of a. You plug a into the function to get the output value. And what we want to identify is that over this open interval that I've drawn centered at a, so if I look at the function just over that open interval, I notice that the function is defined over that open interval. In fact, I can draw the function without lifting my pencil or pen from the paper over that entire interval. And what we want to notice is that f of a is greater than or equal to every other function output on that interval. So this is the big idea. If your output value is the largest value on that interval, then we say that it's a maximum for the function over that interval. This is a local maximum. The local minimum we define in much the same way. We say, hey, can I find an input value a? Let's do a sub 2 to distinguish it from the value a that we have right here. And if I can center an open interval at a, so there's this open interval centered at a sub 2, and if I look at the function just over that open interval, so I focus in on the part of the function that lives over that interval and I ignore the rest of the function, if f of a is less than or equal to every other function output on that interval, in other words, if it's the lowest point on that interval, then we have a local minimum. So this point right here, it would be input a sub 2, output f of a sub 2. And clearly on this interval, f of a sub 2 is going to be the lowest output that you can get on that interval. So this is a local minimum. So taken together, the maximum and minimum values on a function are called extrema when you take them all together. So a person might say to you, find the extrema on a function, and they would be telling you to find the local maxima values, the local minima values, the global values, which we haven't discussed yet. There's some subtleties to finding local max and min. So let's say this function continued on and then it was constant for some period of time. And so we could identify some open interval over which this function was constant. The function would actually be any point you pick on the function over this interval where the function is constant. Any point that you pick is going to meet both criteria. It's going to be both a maximum and a minimum value on that interval. So the way that I like to think about this is, if you're hiking along, the local maximums are going to be the peaks that you would hit along your hike. The local minimums would be the lowest points you hit on your hike. And a valley, when you're walking across a valley, you are locally in both the highest and lowest spot that you can be if it's completely flat. So this is a kind of a special case. In the homework, don't expect me to ask you to have to deal with a constant. I'll always give you something that's really clear cut in terms of where the max and the min values are on that function. So let's take a look at a couple examples. So here we have an example. There's some clear candidates for max and min values on this function. And it probably would make sense to identify the ordered pairs there. So it looks like we're counting by 2's on our tick marks. So that looks like -2, comma 0, input -2, output 0. This looks like it's probably about at 1, input 1, output 2, 4, 5, -5. And here it looks like we're just short of 2, 4, 6. We're just short of 6. So I think in a previous video we said, hey, this is like 5.9-ish or 5.7. Sometimes you just have to estimate. And the output value there is a 2. And here it looks like you are inputting an 8 and the output is 0. And the idea is that we can construct open intervals centered at these input values over which we can clearly identify that this is the highest point on that interval. So if I just look at the graph beneath this open interval, I can see that through this stretch, this is the high point. So this is a local maximum right here. So the maxima for this function, there's a maxima at -2, 0. So this is the location of the maxima, and the max is the output, so is 0. So the local maximum at this location is a 0, and then clearly we could establish an open interval around the 1, and clearly on that open interval this output is going to be the smallest output, so that's a minimum value. So minima. So if we just list the gotta spell it right, minima, there's going to be a local minimum value at the location, input 1, output -5, and at that location the local minimum is the -5. Here I have a maximum, so I've got another maximum at 5.72, and the max value there is the 2, it's the output. And here I have another local minimum value, so at an input of 8 I'm getting an output of 0. So the location of the local minimum is 8, 0, and the minimum is the output value, so it is the 0. So there's really two pieces here. I can give the locations of the maxima. So in this case I've given the location of the two maxima, the local maxima, and then I can actually give you the local maximum values by reporting to you the output value. I can give you the locations of the local minima, and I can give you the actual local minimum values. So one more example that has a subtlety built into it. So this one, it might appear at first glance that there are 3 locations that are candidates for local max and min. Here's a spot that looks like a low point on the function. Here's a spot that looks like a low point on the function. Here's a spot that looks like a high point on the function. The issue with these 2 points here is if this looks like input 5 and the output looks to be -3, if this were to be a local minimum value, we would need to be able to establish an open interval centered at 5 over which the function is defined. But what you can see is that if we try to create the open interval centered at 5, that the function isn't defined past this point. This graph has been cut off right at this point. So this actually isn't a candidate because we can't establish an open interval, and local maxima and minimum require that you establish an open interval around the candidate input variable. So this one's going to fail on this side as well for the same reason. If you try to construct an open interval centered at -5, the function isn't defined to the left of the input of -5. So the only candidate that we have on this graph is this point right here, because clearly at -2, and this looks like input -2, output +4. Clearly at -2 we can establish an open interval centered at -2 over which the graph is completely defined over that entire interval, and clearly on this interval right here that I've established, I actually created the open interval from -3 to -1, and clearly on the interval from -3 to -1, this is the largest output on that interval. So what we have is a local maximum. There's a local maximum at, the location is at -2, 4, and the local max is 4. So again, discriminating between the location of the maximum and the maximum itself, which is the output value, right? This one, there is no local minimum, and it's okay for a local minimum or local maximum to not exist. They don't always exist.